Okay, so now that we've been introduced to the standard normal distribution, let's actually work with some examples that involve standard normal distributions. So one really important thing about Z, or these distributions, is that they come up a lot when we're talking about accuracy of measurement. So as an example, so we'll let Z represent the accuracy of measurements of sound intensity using a signal analyzer. So to break that down, what we're talking about is we have equipment, a signal analyzer, which registers sound as a waveform, right? So here's your sound wave. And a sound wave is analog, so it is literally just the vibrations, the rarefactions and compressions that are then registered by this signal analyzer. And it can tell us all sorts of information about the waveform, including intensity. It can tell us the frequency, right? How fast those sound waves are moving, the wavelength, etc. But each of these things are being measured digitally, and if we're measuring digitally, we may have inaccuracies, so we may have a slight error. So in other words, what we're talking about is if we have our measurements, a zero measurement means that our intensity measurement is right on the money. It is accurate. A positive, so Z being positive, indicates that we're overestimating the intensity. And Z being negative means we're underestimating. So these are the three cases, and we're going to assume that Z is approximately standard normal. So question, what is the probability that a randomly selected measurement accuracy is an underestimation? I'll abbreviate that as probability of underestimation. So in other words, what we're asking for, what is the probability that Z is less than or equal to 0? Okay. So another way of thinking about this is the value of the CDF evaluated at 0. Okay. So let's actually draw the density curve. So that might look like this. Remember that the mean for any standard normal distribution is 0. So we're looking at the left side of 0. And this tail goes out forever, but we're only drawing, a certain part of the distribution here. We're just looking at the typical range. One really important thing about Z is that 0 is both the mean and the median. Median in this context means that the probability that Z is less than or equal to 0 is 0.5. Wait, but that's what we were looking for, isn't it? So this is it. All right. One really cool thing is that not only is this the mean and the median, but it's also and mode. And every agreed upon notion of centrality, every agreed upon measure that is centrality for a random variable agrees for Z. The center is 0. There's no ifs, ands, or buts about it. So another way that this may come up is if we're talking about, and we're going to use what we call a standardized model. So in other words, as we'll see in a later video, we're actually going to be talking about more general normal distributions, but for now we're talking about just standardized. So we're erasing all trace of units, all trace of the original mean, the original standard deviation. We're only looking at z-scores. So any value that is a random value corresponding to a z distribution is a z-score. And one way that this comes up is with body temperature. So z, let's say that's a standardized body internal temperature drawn at random, or drawn from a random individual. So the generally accepted mean is 98.6 degrees Fahrenheit, but what we're saying then is somebody who has a z-score of 0 has the mean body temperature. So mean body temp. Someone who has a score higher than 0, right? So z being greater than 0 means that they have a higher body temp than usual, or than the normal. And somebody with a z-score that's less than 0 is going to have a lower body temp than the mean. So something lower than 98.6, okay? Now, remember that here we're talking about mean. The mean is 0, the standard deviation is 1. So here's a question. What is the probability that a randomly selected body temperature is less than 1.36 standard deviations less below the mean? Well, now what we're saying is what we're looking for is the probability that z is less than or equal to negative 1.36, which is the same as finding the CDF value valued at negative 1.36. So this is not a standard, it's not a typical value that we're interested in, but we have some ways of finding this probability. So one way of doing this is to use a standard normal area table. Okay. So I will take us to a standard normal area table, and just to show you how easy it is to find one, then we will standard normal distribution table. They actually are very common, and they're all very similar to use. Okay, this is not the same one that's in the appendix, but this is the first result that came up on Google. So the idea here then is we're going to search for negative 1.36 in the margins. Okay, so each row represents the probabilities that correspond to, for instance, the first one is negative 3.9, and then each column gives us the second digit after the decimal place. So the first box corresponds to negative 3.90, the second to negative 3.91, 3.92, ... and so on, right? So that means we're looking for the row, which is negative 1.3. That's right there. And we're looking for the column that ends in 0.06. That's this one. So if we look at the exact cell that's in common for those two, we have negative 0.869, and we're gonna round it to 4 places after the decimal. So this is 0.0869. There's another way of finding this where you use a TI-84, and you can use a normal CDF. Just be sure that because we're looking at a left tail for this distribution, so this is our picture of Z, and we're looking at this area, then we're going to need to pick some extremely low value, like negative 10,000, as our lower bound, and our upper bound will be the negative 1.36 that we were talking about. So that means that our arguments for this function is negative 10,000, negative 1.36, 0 and 1, where 0 and 1 represent the mean and the standard deviation. For the exact, if you ever forget the syntax, some of the TI-84s give you the option of having the interactive screen where it tells you exactly what each argument is representing. And there's also a handy guide in the appendix of the book. So, regardless of which method you use, you should get the same value, which is 0.0869. So, roughly 8.7% of the time, somebody's going to have a body temperature that is less than 1.36 standard deviations below the mean.